We left off with the applications of circuits with one source, and this installment is the solution by substitution. So we've gone back and we've looked at these relationships where we were able to solve using linear simultaneous equations. So this is the solution by substitution. So in this case, we've got our two expressions that we solve for I1 and I2. And we do not, you'll notice we do not have an I3 in either of these, so we've got these already set up with the proper currents, unknown currents. So from the first equation, 1419, which is this top one, we solve for one of the variables. Let's take a look at I1. So we're going to take the first expression, we're going to move the terms around so that we get everything in terms of solving for I1. So with doing that, we have 1k I1 that we want on the left side of the equation, everything else we want on the right side of the equation, so that we can then move in the next step the resistance 1k to the other side. So you notice we've got it on the right side in the denominator so that we can divide 1k into 20 volts, 1k into 2k times the current I2, which gives us a solution with I2 in it, 20 milliamps minus 2 times I2. So now if we take this expression and we plug it into I2 of the second equation, 1421, we have 20 volts then is equal to 4k times, well, there's I1. So I1 is 20 milliamps times I2. So we're removing all of the I1 terms out of the expression so that we only have I2 in the expression. When we multiply through by the 4K, we end up with 80 volts minus 8K times the current I1 minus 3K times the current I2. Now that should be I2 and I2 because we got rid of I1. 20 volts then is equal to 80 volts minus 11 K I2. So we combined 8 and 3 together to come up with 11K. So now all we did was move our values from one side of the equation to the other. When we move 20 to this side, we get 60. When we move the 11K I2 to the other side, we get both positive values. So we're set up so that we have I2 that can be divided by 11K here into 60 volts. So I2 is isolated, and we end up with 5.45 milliamps. So doing that, by substitution then, we can take I2, we can plug it into equation 419, again that's the first expression, and solve for I1. So 20 volts is equal to 1K I1 plus 2K, and we make the substitution of 5.45 milliamps for I2, and we end up then with a value here of 10.9 volts. We rearrange our terms so that we have 20 volts minus 10.9 volts is equal to 1K I1. The next step, again, we rearrange the terms so that we have I1 by itself on the left side of the equation, and then we can subtract 10.9 volts from 20 volts. That gives us 9.1 volts. We divide it through by that 1K, and we get 9.1 milliamps. I3 and the voltage drops then can be found as before. So on the next iteration then, we can solve by determinants. Okay, so we're going to the last methodology. So we go back to our equations that we originally had, 1419 and 1421. To start with, we've got it set up. So we have our constants. So there's our K1 and K2. We have our constants for A, 1K and 4K, then become our A1 and A sub 2 constants. And then I sub 2 terms give us 4K and minus 3K. So there's our B terms. So we've got this set up for a second order determinant that we can solve for once we have all of our elements, A1, A2, B1, B2, K1, K2. So the step that they're not showing you is just the setup where we set up our determinants. If you need to go back and refer to that, again, I highly suggest you write that setup down on in your notebook and have it handy because the text here is not going to show every minutia step every time. So jumping ahead several steps, we've got the current I1 then is equal to K1 B2 minus K2 B1 divided by that common denominator that you see in both current terms here, A1 B2 minus A2 B1. Insert then or substitute the values in for each of those elements. Minus 60 times 10 to the third minus 40 times 10 to the third. Okay, so be aware they've skipped a step or two here where they multiplied these terms together, and then we set up our determinant in the denominator, and we have 9.09 milliamps as I2 and 5.545, just like we solved in the previous step with the substitutions for I2. I3 and the voltage drops then can be found as before. So I highly suggest you go back, use this methodology, find that current I3, find the voltage drops as before. Okay, they're shown to you. The problem can be solved graphically, although this method is seldom used in solving electrical problems such as this. It's useful in some applications and is presented here in figure 14.4 as a graphical solution. Okay, so here's the graphical solution. Looks a lot like what we saw in the previous steps where we did the graphical solution of each. Remember that we set up tables for each of the equations and we picked values trying to determine where we can find the point where the two lines cross, where they intersect, and then come up with values close to the origin. So in this case, we have two basic equations, and they should look like this. The current source is equal to the sum of the two voltage drops, V1 and V2. That's going to be from R1 and R2, and the sum of the voltage drops, V1 and V3, across R1 and R3. So substituting those known values, then we get these two equations. We get the equation 25 volts, which is applied, is equal to 680 I1 plus 1.2 K I2. And our values here then of, for the second equation, 680 I1 plus 470 I3. Okay, so we're just substituting those terms into the expression. So the intersection occurs in this case where current 1 is approximately equal to 9 milliamps and current 2 is approximately 5 milliamps. Okay, so this is not an elegant way to solve a problem, but you can see that you can come up with a graphical solution for this type of equation. Okay, as you go through then and do your substitutions, I3 is equal to the difference in I1 and I2. So the equation becomes 25 volts, 680 plus 470. If we substitute that I1 and I2 into the expression here, now we've removed I3 and we've put in the two values I1 and I2. Okay, this allows us to gather the two terms 680 and 470, both current 1 terms, and minus the 470 current I2. Now we need to multiply or divide the equations 1423 and 1425, there's 25, 23 from the previous screen, by some factor or factors that make the coefficient of I1 or I2 both equal in both equations. So as we know, there is an infinite number of factors that we could use. We choose to multiply the equation 1425, that's this equation here, by 2.55, so that the coefficients of I2 in both equations equals 1.2. Okay, so this is something that you have to look at, and by inspection come up with a term that you might multiply through. Okay, so you can see there's a lot of work involved in doing this based on the graphical solution. So the next step, when we multiply through each of the terms by 2.55 from equation 1425, we end up with 63.8, 2930, and 1200 as the coefficients for each of the terms in this expression. So now we can take the original number one equation, 25 volts is equal to 680 by 1200, which are our coefficients and our resistances and our applied voltage. And then we can add the terms together in this case so that we can eliminate. So the whole idea behind multiplying through by 2.55 is so that we could set up the expression so that when you added them together, we end up with a difference of 1200 here and 1200 here. It cancels out, and all we're left with is I1. So 88.8 volts is equal to 3610 times the current I1. Solving through for current I1, we get 24.6 milliamps. So now having that, we can plug that I1 back into the original equation. So we're going to go back to equation 1423, which had the two original resistors in here as our coefficients. Plug that value of 24.6. Now we have the expression set up so that all we have left for an unknown is current 2. So gathering our terms, moving them to the left and right as required, we end up with 8.3 volts divided by 1200, just by moving this over, is equal to current 2, or 6.92. Okay, so in this example then, we have our currents that we just solved for. Current 1 then is equal to the sum of I2 and I3, because remember what we had here was a series parallel circuit. You'd have to go back. I'll see if I can go back here to remind you. There it is. There's your series parallel circuit that sets us up for these current equations. Okay, I3 then becomes the difference of I1 minus I2. Why? Because of the split that occurs right here at the node. Part of the current goes this way, part of the current goes that way. So then I3 is equal to 24.6 minus 6.2. These are two values that we just solved for. If we go back here and look, there's 24.6, there's 6.92, and we end up with a current for I3 of 17.7 milliamps. That's the current through that resistor after it splits from the total. Now we can look for the voltage drops across each of those resistors. The voltage drop for 1, IR, is equal to 16.7. Voltage drop 2, IR, is equal to 8.3. Voltage drop across V3 or resistor R3, IR, is equal to 8.32. So we can solve then for each of our voltage drops at this point. Now it looks like the book is shifting gears here. They says let's solve the same problem by using the determinant. So in essence, we've started over again. So let's stop there, go to the next session, and start over again looking at the determinant solution.